We can start this morning session. And so we have Igor with his lab lecture on the polar condensate.
Yes.
So, thank you.
Comment? On démarre? Yes. Okay. So welcome back to this last day, everyone. So I will go on with my lectures on dipolar Bose-Einstein condensate, and I want to recap a little bit where we were last time. So I showed you that with the mean field approximation, if I make a Bose-Einstein condensate like this, then dipoles are aligned and the dipole-dipole interaction is attractive. And if I have epsilon dd, which is the dipole length divided by the scattering length, which is bigger than 1, then the prediction is that to minimize the energy, the Bose-Einstein wants to maximize its density, so it leads to a collapse. The gas wants to implode on itself. So this happens in the case where I make just one big condensate and I align the dipoles like this, or if with the trap we can force the density distribution to be like this initially, but sometimes you have some instabilities, and these instabilities then lead to droplets that are also aligned like this, and so individually they all want to collapse in order to minimize energy. Okay? So then the question is what happens in reality, because energy is not infinite. So the first mechanism that I mentioned is three-body recombination. If I have three atoms that come in contact with each other, then this leads to formation of a molecule, and this is what we call three-body losses because the energy is released and we lose all the atoms. And it's characterized by an equation like this. And by a little bit of math, you can put this into the Gross-Pitayevsky equation as an effective imaginary term. I will put this back in the future slide. So this is one mechanism that happens at high density, but we saw also another thing that we have to take into account is that the Gross-Pitayevsky equation is derived using an approximation, and this approximation is valid only if square root of NA cubed is small. Okay, so we call this usually the mean field approximation, but when we go beyond the mean field approximation and keep some fluctuation of the bosonic field around its mean value in the Hamiltonian, we can calculate the energy at the next order. Okay, and so this comes physically. This comes from the fact that if there are interactions, then the ground state is having zero excitations in the system. It's having, if you want, it's to have the vacuum of phonons in the system. But this doesn't mean that it's all the atoms at zero momentum, because these quasi-particles, these phonons, they don't correspond directly to atoms, and so if I look at the ground state, basically it doesn't have a mean population. This shouldn't be exactly this formula. Basically, it shouldn't have a mean population of atoms. It shouldn't have all the atoms in the ground state. There should be a population of atoms in the excited state. Okay, and so the first time this was the effect of this was calculated was by Li, Wang, and Yang, and they calculated that the energy is shifted, and that indeed some atoms are not in the condensate. And as I showed you, this was measured in an experiment actually not so long ago, and we discussed that it's surprising that it's a plus, but I won't go further on this. So now this was all for contact interacting Bose-Einstein condensate. So if I forget that they have a dipole, but my whole lectures are about dipolar Bose-Einstein condensates. So actually I have to take this into account for the quantum fluctuations. So the energy that is added by keeping into account quantum fluctuation is calculated by accounting for the vacuum energy, so the fluctuation of each mode in each of the phononic mode. So because the dipole-dipole interaction here modifies the dispersion relation, you remember there are some directions where I have a strong dispersion relation, a high speed of sound, and some directions where I have a low speed of sound. Then this will modify the energy of the vacuum of phonons when the calculation is done. So I will absolutely not show you how the calculation is done. It should be a whole lecture to do that. If you want references on how to calculate this, I can give them to you per email. And basically, I'm just giving you the result. And the formula is here. To sort of give you a taste how this works, basically, before it was isotropic, and now we have exactly the same thing. So things don't change so much, but the dispersion relation becomes anisotropic, and this anisotropy then leads to a correction when I average over all directions. So this correction here, you see this is the same formula as before, but I have a Q5 function, and this Q5 function is just an average over all angles of this expression here. So in the case of for the energy, it's Q. So this is to the power 5 halves, but for the quantum depletion, for the population of atoms that are not in the condensate, it's Q3. So you just have to do the math and you find that it's 2 different powers. But basically, the important thing is I have the same thing, but I have an extra factor, and this factor is in the region where epsilon dd is not huge. I can take the lowest order expansion, and it's 1 plus 3/2 of epsilon dd squared. Okay, so if epsilon dd is of the order of 1 or 2, I get an increase of the quantum fluctuation term by factor 2, something like this. So the effect of quantum fluctuation is stronger, and this is actually because the dipole-dipole interaction creates mode in the system that have a high speed of sound, and so their mean energy is high. Okay, so this is the effect if I take a homogeneous isotropic Bose-Einstein condensate. You can calculate this, but in reality it's never the case. In the experiment, it's never infinite homogeneous isotropic. I make trapped Bose-Einstein condensates in my experiments, so I have to take into account the fact that the density is not constant. Okay, so it's non-homogeneous. And there, so far, there is no good theory, or there is no perfect theory that tells us how to do this properly, but we use some approximation. So one is the local density approximation. Okay, so basically I will assume that I can locally calculate the energy of the quantum fluctuation term and use now space varying density. Okay, so rather than calculating the whole spectrum for the whole system and calculating the energy of the whole system, I will say, okay, locally I have a density, and this density then gives me a local shift of the energy, and I can plug this into then my non-homogeneous case. And so basically, in principle, this holds only if the gas has a density that doesn't vary too much on a scale that is large with respect to the hidden length. Yes. And there is a second assumption that I have to make, is that the quantum depletion is small, because I don't know how to take into account the quantum depletion. The atoms that are not in the condensate I have no idea how to take them into account, to have equations on the dynamic or only simply on the energy. But basically, if I make these two assumptions, I can put an effective term in the Gross-Pitayevsky energy functional that is related to the interaction. So remember here in the Gross-Pitayevsky equation or the Gross-Pitayevsky functional, phi squared is equal to the density, okay? And for the local energy at a given density, I have something that's Gn squared over 2 plus blah 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 plus, so the beyond mean field is some term that I could call eta, okay? We call it LHY for U1 the person to calculate it, and I have the square root of Q times this Q5 function. And so this scales like density to the 5 halves, okay? The correction to the mean field, so here I have the mean field term, and the correction to the mean field has an extra square root of n, so rather than being n to the second power, it's n to the 5 halves. And so if I write the energy functional in terms of this phi here, which is the wave function, I have 5 to the 5th power. I don't know if you can read it easily. So the mean field is 5 to the 4th, density squared, and the quantum fluctuations have an extra power of phi or an extra power of phi. So in the end, I can also rewrite this in the Gross-Pitayevsky equation as an effective Gross-Pitayevsky equation. I have the usual mean field terms, and I add an extra beyond mean field term that has 1/2 power of n or 1 power of phi more. Okay, and the prefactor is what was shown in the previous slide. So here is the whole equation in the approximations that I gave you that should describe the whole dynamics of the Bose-Einstein concept. It's a Gross-Pitayevsky equation that is we call it generalized or extended by this beyond mean filter. So remember, this is really an approximation. So we have to verify either by comparing with experiments or by comparing with more advanced calculations like quantum Monte Carlo, that it's actually correct to say I have a Gross-Pitayevsky equation that corresponds to the mean field approximation. Now I know that if I calculate only the energy in a homogeneous infinite case, isotropic, I get a shift, and now I can take my mean field approximation and add some effective term. So this is not obviously correct. This has to be checked. So I have the beyond mean field term and the 3-body. Okay, and these terms, they act at higher density. Okay, here I have phi squared, so it's proportional to density in the Gross-Pitayevsky equation, and here I have phi cubed, so it's density to the 3 halves. Okay, and for the 3-body losses, I have phi to the 4th power, so this is density squared. So I have 2 terms that now will act at high density. So when this wanted to collapse and have infinite density, then these terms will be important because they have a higher dependence on density. This equation, yes?
Excuse me, you probably told us earlier, but I forgot. The L3 is heuristic or is it calculated?
No, it's completely, there is...
From the experiment?
Yes. So I think for alkalis, only Paul Julien is able to calculate L3 from the van der Waals potentials. In the case of dispersion, you have to take 160 van der Waals potentials into account to calculate the 2-body problem. And I know Paul Julien is not able to calculate L3 because we discussed it before. No, so but this is not very hard to measure in the experiment. L3 is you just make a gas at a given density, and you wait. Yes, you wait, and you can see So initially it's the free body losses, and then as density goes down, you have more losses. So this is a beautiful equation that I can plug into a computer, and this will give me the answer, but it's good to have a feeling about what will happen. And so the question that we can ask is, what will play a role first? Will it be the quantum fluctuations or free body effects? Okay, so free body effects, they're imaginary. These free body losses, they lead to a depletion of the gas as a function of time. The atoms very quickly leave the gas because the density is high. Whereas this is conservative. Okay, this is something that will not create losses, but that will change the dynamics. Okay, and this is, as opposed to the effect of dipole-dipole interactions, this is always repulsive. Okay, so it always costs a lot of energy to increase the density due to the effect of ions. Okay, so I need to ask the question: who comes first? Whether I will see the effect of this or the effect of this, or whether I have to take both into account. So to know this, basically, I need to know the scattering length, the dipole length that will give me the strength of the mean field terms, and the strength of the beyond mean field term, because it depends only on the scattering length and on the dipole length. And I need to know these free body losses that the only way to know is to measure in the experiment. Okay? Remember, so they will be important if epsilon dd is bigger than 1, because that's when the gas will collapse, density will go to high values, and so these terms will be important. So I'm taking an arbitrary value of epsilon dd is equal to 1.6. Okay? So let's look at some concrete atoms that are used in the experiment. The first one that was used was chromium. Okay?
Can I ask a question?
Yeah?
Do you recall the Bose-Nova experiment?
Yes.
And then you have a negative scattering length, and then you only have the free body term.
Yeah.
So by tuning the dipolar interaction here, you can induce a collapse or not a collapse, and then you either have the Bose-Nova type of physics or space.
Yes. How long are you staying? You?
I'm still here.
Okay. If I see you leave before I answer your question, I will answer it.
Okay.
So, for chromium, the dipole length is 15 boradii. Okay? And so in order to have a collapse, I have to make the scattering length smaller than the dipole length. So I have to go to small scattering length. Okay? Then the mean field terms will be negative, and this will predict a collapse. But then here, look, this is proportional to a to the 3/2, and I have an extra a factor here. This is the coupling constant that is proportional to a. So basically, since a is small, the beyond mean field term will not be very big, because a is not 100 a0 or something like this, but it's quite small. Okay, this Q5 of epsilon dd depends only on epsilon dd. I fixed epsilon dd is equal to 1.6, so Q5 is approximately 3, I think, in this case. So I have beyond mean field term that is not very huge because A is not very large. And for chromium, I have to give you L3, which is 2 10 to the minus 40 in SI units. That was measured experimentally. Now let's go to erbium, which is another atom that is used in the experiment that has a strong dipole interaction. Now the dipole length, so this is given only by the dipole moment and the mass, is 67 boradii, so it's already bigger. Okay, so to go to epsilon dd is equal to 1.6. I have to go to a scattering length that is lower, but it's not it's not as low as before. Now it's 42 boradii, so this term will become bigger again because this is proportional to a to the 5/2, so this grows quite fast with a. L3 is basically in the same ballpark. It's 10 to the minus 40, a little bit more favorable. So this term is a little bit smaller, but it's basically the same as for dysprosium, for chromium. And finally, if you take dysprosium, the dipole length is again twice bigger than erbium, so it's 131 boradii. So it means that to go to epsilon dd is equal to 1.6, I have to go only to A is equal to 82 A naught. So it's again twice bigger than erbium. So this term will be even larger than for erbium and chromium. And this is also a huge advantage because for the experts, in order to have a dipole length that is larger, significantly larger than the scattering length, I don't need to use a Feshbach resonance. This is already the case away from Feshbach resonances. And Feshbach resonances, they're very nice, but they increase the losses. And in our case, we can stay away from them and have, or we can stay in a region where the losses are not very strong. So we have free body losses that are almost an order of magnitude smaller than in the case of erbium and chromium. So dysprosium has a huge factor here with respect to chromium, and this is much smaller. So let's look at these terms. Okay, I plot these terms for the different atoms. Okay, so I plot the strength of the whole mean field. Okay, the absolute value, the strength of the dipole of the beyond mean field effect in absolute value, and here also. So this term is of course imaginary, but I plot the magnitude. So the blue line is the mean field approximation. The red line are the free body losses as a function of density in log-log plot, and the yellow line is the beyond mean field terms.
I have a question.
Yes?
You Raven now is here.
Ah.
That's a comment.
So we should
No,
wait
no,
for
no.
bye. So
Au revoir.
safe travel. Okay. Good. So I answered this question already. So here you see for chromium, when I increase density, mean field increases. Okay, so it would shoot to infinity if there was nothing else. But the free body losses, okay, so the absolute value of this term as density increases become sizable, and at some point they cross. So the effect of the mean field and the effect of the losses will be more or less the same as density increases. And where they cross tells me when basically things are going to be different from what I expect only in the mean field approximation. And you see that basically, so these losses will be as strong as the term that creates the collapse. So basically, I will lose the atoms as soon as these guys cross. And you see the beyond mean field effects are, this is in a log-log plot, so they're more than, they're more than one order of magnitude smaller. Okay, so I can completely neglect these guys because here you see that they're very, very small with respect to the effect of losses and the effect of beyond mean field. So in the case of chromium, in these conditions, I can completely ignore the beyond mean field effects. It will be only, the dynamics will be only driven by mean field and free body effects because the beyond mean field effects are very small. In the case of erbium, now the situation is different. You have the mean field term here, you can see, and you have here in yellow again the beyond mean field, and here you have the losses, free body losses in red. And so you see that now the hierarchy is inverted. You have first beyond mean field effect that will be on the same size, the same strength in this equation when density increases as the mean field term, and then free body losses will play a role. So here you cannot neglect beyond mean field effect. They are very important, but unfortunately free body losses are not so small that you can completely ignore them. Okay, you have maybe a factor 3, a factor 5 between the two, but they will still be important. I can't just rule them out of the equation. You see that the red line is lower, but not so much lower. So basically, density will increase here until the effect of beyond mean field will be important because they will be on par with each other. But at this point, free body losses cannot be neglected. And finally, dysprosium. Here the situation is absolutely marvelous in my opinion. because here you see mean field again, beyond mean field, and free body losses. And as density increases, you see that beyond mean field hits the mean field line, so the effect of beyond mean field, the beyond mean field term will be at the same level as the mean field effect at a very low density with respect to the one where the free body losses will be. The free body losses are extremely weak in dysprosium. So this is really a wonderful effect where beyond mean field will really dominate, and these losses, you can't completely ignore them because little by little you will lose atoms, but this will not modify the whole dynamics. They are just a small term that is 2 orders of magnitude lower than the 2 other terms. So this is really a very interesting situation where you will have only the conservative terms that really play a role in the dynamics with this question. Okay, so now we have 2 different regimes. One that we have with chromium, where free body losses will change the dynamics when you have a collapse, and one with dysprosium, where beyond mean field effects will change the dynamics, and in the middle you have erbium, where both effects are important. So let's start with chromium. With chromium, I have my whole Gross-Pitayevsky equation, but I showed you that the beyond mean field effect, so the term that I had on top here, I can completely ignore it, and I keep only the effect of free body losses. Okay, so here what happens is you have a collapse of this cloud, okay, but this collapse is sort of anisotropic because what drives the collapse is the dipole-dipole interaction. Okay, so the atoms are attracted to each other, but they want also to minimize their distribution, so they will have a shape that changes and a density that goes to infinity. And so as soon as density goes to infinity, then L3 here times the density to the square with the imaginary term here will completely deplete the gas. So you will lose atoms very fast when density goes to high values. Okay, and so what happens in reality is the following: so the cloud implodes very fast. When density is very, very high, you lose atoms very, very fast. The atoms they form molecules and they disappear from the cloud very, very fast. And at some point the density goes to, so this drives the density goes to very small values. And when the density is very small, all these interaction terms here, they become small. And what you have to keep into account is kinetic energy. Okay, so you have a collapse. And so this collapse creates a very, very tiny density distribution in the center that is very dense, which the density goes down, and you have not now density as a function of position. You have something that is very peaked here at the center. Okay, so when you have a very peaked density distribution or a very peaked wave function, you know that kinetic energy is very strong, and at some point kinetic energy is very strong, so it wants to explode again, right? Because this is you know, when you have a wave function that is very big, you have basically you have quantum pressure, what we call quantum pressure, that pushes the atoms again towards lower density, and this is exactly what has been observed. What they saw was that it initially collapses, and then it explodes again, and this explosion here is actually just a reflection, and it's really beautiful because when it was collapsing, it was not collapsing in all directions the same way. It was driven by this anisotropic dipole-dipole interaction, and so when it explodes again, it's just a reflection, and so you see the anisotropy of the dipole-dipole interaction in the explosion that follows the collapse. So when we look at the collapse, it's too small, we cannot see anything when we zoom on this because we don't have the optical resolution in the experiments to see this. But when it explodes, it's just a reflection, so it reflects exactly the collapse dynamics that you had before. So you see this beautiful explosion with this typical symmetry of d waves, which is just this function here, and with simulations of this equation that keeps only three velocities into account but forgets about the unknown field, you have a very good agreement between experiments and theory. Okay, so with chromium, and here, as I told you, the density goes to very low values very fast, and then it explodes again, and you get the same. It's not the density, so it's the total number of atoms. You lose a lot of atoms during the collapse. You see, this lasts for a very small time. It's 400 microseconds, and then it. Okay, so for chromium, the system is unstable. It collapses and then explodes again, but I cannot keep it in my car. So let's go to the case of dysprosium now, where I can ignore these three body losses, at least in first approximation, and I have only a beyond mean field effect. So the effective energy, the Gross-Pythaevsky functional, looks like this. Okay, I have this beyond mean field term, and let me write only the effect of interaction. Okay, so I have the energy here, which keeps kinetic energy and potential energy into account, but I will only look at the interaction energy. Okay, so here these two guys are the mean field terms, and this is the beyond mean field term. Okay, and this is still too complicated for me. At least, so I can do numerical simulations of this, but to have a sense of what's happening, I want to have a simple picture. And this is still too complicated, so I will simplify it. I will look at the energy per unit density. Okay, so basically this gets rid of the integral here. I look at the local energy per unit volume, or per unit density. Sorry, energy per unit volume. Okay, so the local energy per unit volume at a given position, and I will look at this at the center of a density distribution that looks like this. Okay, so I take a small volume here, and I look at what is its energy. Okay, so this gets rid of the integral. So remember this phi dd here is an integral of the interaction, dipole-dipole interaction over the whole density of the cloud. So every piece of density interacts with the whole density. So if I look at now locally how the density at center interacts with the whole cloud, I have to integrate over the density of the whole cloud, but this can be done. And what you find is that this phi dd term here is actually proportional. Okay, that's too late to say it, but that should be a term. So it's proportional to phi dd of 0, okay, which gives me the interaction at the center is GE, okay, I will tell you what GE is, times the density times f of kappa, okay, and remember kappa is the aspect ratio, okay, so if I have R, and Z, kappa is R, Z, no, R over okay, so with the minus. So when the density is elongated like this, such that this is very small, f of kappa is almost 1, so I have basically minus GGG times n. Okay, but I can also keep the f of kappa. This is not a problem. So and GDD is proportional to the scattering length, to the dipole length. So now I can rewrite finally I can rewrite the local energy per unit volume at the center of the cloud as a mean field term, okay, that because I have the density here and I have the density phi dd, here I have the density squared, so the mean field term is proportional to density with a prefactor that is 1 minus f of kappa epsilon dd. Okay, so this is what we found also when we look at the total energy in a droplet that has a Gaussian density, for instance. So I have the mean field term that is the difference between the effect of contact interaction and dipole-dipole interaction. Okay, because here what I did was to factorize the contact interaction, and I didn't write it, I just wrote proportional. But here there's the G for the contact interaction, and the ratio of G dd over G is exactly equal to epsilon dd. And I have my f of kappa that remains. So I have a reduced mean field, and if epsilon dd is bigger than 1 and f of kappa is approximately 1, then this mean field is attractive. That's what we found in the last lectures. But now what is very interesting is that the beyond mean field is here. I can easily calculate it. All I need is density to the 5/2. This comes here. Epsilon dd I know A. I can factorize it. So basically, I have a beyond mean field term. It depends on A actually. I should be careful. I have a beyond mean field term. If I factorize n squared, there has an extra square root of n factorial. Okay. So I have one attractive term that has a dependence on the density that is n squared, and one repulsive term. This is always positive, so the energy always increases according to this term when density increases, and that has a higher dependence on n, so it will play at a higher role at higher densities. And what is very nice in this case is that because the mean field terms are individually not so small, because I have large A and large ADD, then the beyond mean field effects are still strong. Okay, they are actually amplified by the presence of the two interactions. And so let me write this energy per unit volume as a function of density. If I didn't have any beyond mean field term, this would go down to infinity. Okay, and I would have the collapse that I told you about. But now, because I have this beyond mean field term, at some point it goes back up, okay? So to minimize its energy, actually, it doesn't want to go to infinity because to infinite density because the energy would be infinite, but the energy is minimized at a finite density that is not infinity. Okay? So basically, what this tells you is that this feels an attraction that wants to have a high density. But at higher density, you have a sort of short-range repulsion. If the atoms get too close, they repel each other. And this is exactly what happens also in a van der Waals liquid. So you have long-range attraction, and then at short-range you have repulsion, so that the atom from a liquid that binds itself. Here, it's a little bit different because this is not in the two-body interactions that I have long range and short range. It's really a many-body effect that leads to the same kind of phenomenon where I form a liquid that has a fixed density. And what is interesting is that this equilibrium density is given only by the interactions. If I minimize the energy with respect to density, I find that it's given by the ratio of these two things. And what's important is that I can calculate this ratio because I know the scattering length and I know the dipole-dipole interaction in my system. Okay? I want to note, and I will come back on this at the end of the lecture, that this was, we did not invent all of this. We observed it in the experiment and we realized that it was proposed actually before we observed it by Dima Petrov. So it's the same Dima Petrov who did this effective narrow resonance model that Jörg Raben told us about. So it's a good habit to read his papers. Okay, so now let's see how this modifies the more carefully things with respect to chromium. So if I use a Gaussian ansatz, remember in chromium I have if I look at the energy as a function of, I make a Gaussian ansatz, so I have a droplet, okay, and I use these sizes as variational parameters. Then I have an energy landscape that looks like this, and sometimes I have a metastable solution, and then I have something that is unstable when I am trapped. And at this instability, we saw what happens. I have this collapse and this explosion again. So this was for chromium, but now for diffusion, it's completely different. Okay, what happens is, so here this is the same thing that is plotted as a function of the sizes, the energy here. And I don't know if you can see, but there are now two minima. So this is in a trap where I try to force the atoms to be side by side. So there is one minimum where the size R is bigger than the size of Z. Okay, so I can make it flat by forcing it with the trap, and now the dipole-dipole interaction is repulsive, such that there is no collapse. But I can also have a solution which doesn't really care about the trap, still goes like this. And in the case of only mean field, I would have a collapse. But now I have a minimum of energy, as I showed you, because at high density I have this beyond mean field. And what is quite interesting is if you look at the density that you get from minimizing the energy with the Gaussian ansatz, as a function of the frequency of the trap, so if you try to compress the atoms, here this guy is sort of soft. It's really it's a gas in the sense that it's very compressible. If I increase the frequency of the trap, so if I try to compress the atoms, they will compress, right? The density goes to higher values, and actually this, you can easily describe this. This is exactly what you expect for normal Bose-Einstein condensates. On the other hand, this solution really doesn't care about the trap. Density is flat, as if I compress, it doesn't compress. So it's not completely incompressible, but it's very weakly compressible. So you really have the same kind of differences as between a gas, which if I want to compress, accepts to be compressed, and a liquid which doesn't want to be compressed. The reason for this is that here I am at an equilibrium between attraction and repulsion, and the density is not really given by the trap. Whereas here everything is repulsive, so the atoms, if I would let them in infinite volume, they would just expand forever. Okay, and this is also as a function of atom number. You see here at low atom numbers, so this is only for the liquid-like solution. As a function of atom number, for low atom numbers, the effect of kinetic energy has to be taken into account. It's not completely flat, but then it becomes completely flat. I can increase the atom number, and it will just grow in size to keep the density constant. Okay, and so I have these two kind of solutions. So I plot here now the sort of phase diagram when I have a trap. Okay, so here is the trap aspect ratio. Remember, the trap aspect ratio gives you the ratio of the frequencies along the dipoles and perpendicular to the dipoles. So when lambda is big, I am trying to squeeze the atoms like this to make crepe, pancake. Whereas when lambda is small, I allow the atoms to go into an elongated density distribution, a cigar-shaped cloud. Okay, and so here is the phase diagram. When I have very high scattering length, the contact interaction is repulsive, so that the dipole-dipole interaction is not strong enough to drive a collapse, to have a refractive cloud. So I have a repulsive Bose-Einstein condensate. When the trap aspect ratio is large, it looks like this, like a pancake. Okay. Here I have a region which corresponds to what I showed you before, where there are two minima that are possible. Okay. Either I can have something that is repulsive, that looks like a pancake, but also something that is that has a cigar shape and that has a very high density and that is attractive. And there is a region where I have a crossover between these two things, where they continuously turn into they continuously turn into one another. So here I have this bistable region. And here, when I go from here to here, the fact that it's bistable is a hint that we will get a sort of instability between the two. And actually, you can show that here you get exactly the modulational instability that I told you about before. Okay, so you start with a cloud that is flat, and you try to go down. You try to go down in scattering length, and at some point, rather than jumping smoothly from this minimum to this minimum, it has this modulational instability that creates many droplets. Okay, so here is a movie of numerical simulations of how we got this in the experiment. So the cloud is initially has a pancake shape, and we do exactly what was plotted in the previous slide. We lower the scattering length to go into the bistable region, and you see that you get this instability that creates many droplets. Now what is new for this lecture is that now these droplets are stable thanks to the beyond mean field expulsion that acts as magnets. Okay. So you see that they arrange also, so these images are looking at the same thing from the top, and so they arrange also in this sort of triangular lattice shape. Okay. But now, okay, so this was the first time we observed this. We just wanted to test that indeed these droplets existed thanks to the beyond mean field term. So we changed a bit the scattering length to change the effect of the mean field term and the beyond mean field term with respect to each other, and we checked that the density behaves as you would expect. So you change the density with respect to you change the scattering length with respect to reference scattering length, and you see how the density changes with respect to the density of the reference scattering length. Error bars are huge, but the scaling is actually quite high. We change the scattering length by only 6%, and we have more than a factor of 2 in density, and it's completely compatible with this simple argument that I gave you in terms of minimizing the interaction energy in the system. Okay. Maybe I should repeat that again. Okay, so I showed you what happens here. Now it would be fun to actually try to go here and create only a single droplet. Okay? Because here it's because I'm going into this bistable region where I have 2 minima and I can't smoothly transform the system into one big quantum droplet. But actually all you have to do is change the aspect ratio of the trap. So stop forcing the atoms to be side by side, but let them be head to tail, so elongate, and then lower the scattering length. And this is what we did. And you see here, rather than having all these many droplets, at the end what we get is a single droplet. And so we have also played with the trap aspect ratio. We can easily modify the trap in the experiment. And we looked, so the color is artificial color. So sorry, it's not the same color code, but it's the same thing you see here, here, here. And by changing the trap aspect ratio, we see that we create single droplets, and then at some point, puff, we start creating many droplets. And so if we look at the trap aspect ratio at which this happened, it's in very good agreement with what you expect from the phase I just want to show you what it looks like from the side, because every time I show these droplets to you from the top, and I tell you, believe me, they look elongated, but we can look at them from the side. And so initially, you see, when the scattering length is high, they're not very elongated, but then as we lower the scattering length, we have something that is very elongated like this. So this is the same thing as before, but now I look from the side. Okay, so they do look like this. And you see that they live for a very long time. Okay? I want to mention that this works also for erbium. In erbium, I told you the 3-body effects are important, but this was quite an important check, that if you really include all these terms in the equation and do numerical simulations, for most parameters, for for most things that you can observe in the experiment for the atom number, as a function of time, as a function of scattering length, it works. In terms of density, it's not more precise than what I showed you before, but actually for erbium you really have to take everything into account, otherwise it really fails at describing what is. So this was done in Innsbruck here, let me summarize a little bit. I have two possibilities in the system. I can have, if I force the atoms to be in a side-by-side distribution, I have a repulsive gas, okay, and the trap is needed. If I release the trap, the repulsion of the atoms will push them far away from each other, and so they will have a zero density if there is no trap. Unless, of course, you have this instability that makes droplets, but if I forget about this. And then I have another possibility is to have this elongated density distribution, in which case the density is only given by the balance between attraction coming from the mean filter and repulsion coming from the middle mean filter. So the simple question is, do I need any trap now? Because in all quantum gas experiments you need a trap, because of course what you have is a gas. So if you remove the trap, then the atoms, just like the air in this room, will fill the whole volume, and we have a few thousands of atoms, so you will never see them if you have a volume that is even just a cubic centimeter or something like this, because the density is extremely low with respect to, for instance, the air in this room. But now it's a different situation, because they are sort of self-trapping in principle. The trapping comes from the attraction between the atoms, and they don't collapse thanks to the mean field effect. So the question we wanted to ask is basically, if you take it out of its container, does it remain self-trapped like this, right? So this is a French cartoon, okay, where they go in space, and actually is the liquid leaves the glass, the container, but you see that it remains, it forms a droplet that is self-bound. So basically we wanted to do exactly this experiment with our constant. There were two theory papers that predicted that yes, if you remove the trap, so if you keep everything into account, and you remove the trap, then you have indeed a solution at high atom number where you have a self-bound BC. So what does this mean? It means that if I look at one atom inside the whole droplet, this atom feels a trapping potential that is created by the attractive interaction of all the other atoms in the droplet, and this trapping potential holds a bound state. Okay, so basically this is a self-consistent problem where you can find a solution where the density is like this and traps itself. But there is also at lower atom number a region where you don't have enough atoms. So if you look at one atom inside, there is a trapping potential that is created by all the other atoms, indeed. But if the atom number is too small, then there is no bound state. And this is because if you have a trapping potential, there is not always a bound state in quantum mechanics. The trap, in 3 dimensions, the trap needs to be deep enough. You have a high enough volume. Here, at some point, as you lower the atom number, the attraction is too weak, and you can't counteract kinetic energy, so point pressure, and that forbids to have a bound state. So there is no bound state, and the atoms cannot bind to each other, and you have a gas. You need the trap to keep it okay. So we wanted to check this in the experiment. Sorry. So here in green and red, what I represented are the lasers that we use to trap the atoms. Okay. So the atoms are attracted by the maxima of light intensity. So we create a light intensity landscape that has a harmonic dependence such that I can create a droplet. And then all we do is we just switch off the trap, and we look at whether this droplet expands or whether it remains at a fixed density, like in the cartoon. The only trick that we had to play was that if you do this, the droplet falls, obviously.
But if we turn off the magnetic field,
Sorry?
if we turn off the magnetic field,
We turn off the lasers,
the laser, not the magnetic field,
we turn on a
on.
magnetic field.
Okay.
That has so we always have a magnetic field like this, but we add a spatial dependence to a weak spatial dependence to the magnetic field. So we have a gradient in the magnetic field that is non-zero. Okay. So a gradient of B is non-zero, and so what you have is a force that is given by this. No, sorry, I shouldn't. The force is like this. Okay? And why do we do that? It's because if we don't do anything, the atoms fall, and we can't image them when they fall, because they have to be exactly at the right position for our microscope objective that looks at the atoms. They are in vacuum, but we have a lens that allows to look at them. And if they fall, we don't see them anymore, so we switch on a magnetic field gradient such that they levitate and they don't fall down. Okay. And here is what we observed. And to me, this was I think this was the most beautiful experimental results that I've seen. So we see here, you see initially there is one droplet, and then there you see a little sort of cloud around the droplet. But as we wait in time, so at t is equal to 0, here we switch off the trap. And we see here that the droplet remains small, so it does not expand for tens and tens of milliseconds. And at some point it expands. And if we do this at a lower atom number, we see that the droplet is self-trapped, and at some point it starts to expand again. So for me, this was really incredible. Okay, so to tell you the story, that the student is Matthias Wenzel. So his name is Matthias Wenzel. We saw the papers. They said, yeah, there should be a self-bound state. And I said, I don't believe in this. We don't have high enough atom numbers. We will never see the self-bound state. I went to Hanover. I discussed with one of the theoreticians who predicted this. He told me this, and I was very skeptical. And then I came back. In Stuttgart, the student told me, yeah, I have this close-P-T-S-K simulations. I put all the terms with the three-body losses. It should work. I said, it will not work. And then this was a Friday, and I came back on the Monday morning, and he came on Sunday evening, and he did take this he did make these droplets. So I was completely, for me, this was absolutely incredible. So he started by making the 20 milliseconds, and then we sat in the lab and said, okay, let's go to 50 milliseconds. We still saw it. 70 milliseconds, we still saw it. And actually, it goes on to, we saw sometimes some droplets after 100 milliseconds. And for an experimentalist, there are not many, but for an experimentalist, this is a very, very, very long time. Without a trap, in principle, you never see the atoms because they always expand and you don't see anything. So for me, this is almost as beautiful as this that we saw yesterday, almost. But this is more beautiful. Good. So let's try to explain what happens. So here, you see that the atoms remain self-bound, but at some point they expand. So this video of the simulation explains what happens actually. So you see here the atom number as a function of time, and here the size in the radial direction. Okay, and here you see what the density as a function of this direction looks like. This is not very important. So we keep everything into account. So the droplet exists thanks to this attraction and repulsion that I told you about. But there are three body losses that drive a slow decay of the atom number. And at some point you hit the atom number where you saw before there is no self-bound state anymore because the density distribution is not strong enough to keep a bound state. And then at some point, hop, when it crosses this atom number, it starts to expand and you see that density goes to infinity. And this is exactly what we observe. Density goes to 0, sorry, the size goes to infinity. And this is exactly what we observe in the experiments. At some point, it starts to explode. And if I change the initial atom number, I start at a lower atom number such that I cross this critical atom number at shorter times, I observe exactly this, that this explodes a bit earlier. So if we look at the atom number as a function of time, it goes down, it goes down, it goes down. This is because three body losses deplete the cloud, and at some point it reaches the critical atom number, and there the density goes to zero very, very quickly because you saw that the size expands very fast, right? And because three body losses scale like density to the cube, density goes to zero, so you stop losing atoms right away. And then the density, the total atom number remains constant. And we can measure like this the critical atom number. And so we can change a little bit the scattering length and explore this phase diagram that I showed you, where you can have a self-bound solution or expanding gas. And here, so you see here this dashed line, these are results of the Gross-Pitayevsky, the extended Gross-Pitayevsky equation with the BL mean field term and three body losses. And here is the experiment. We did it with dysprosium 164 and with dysprosium 162, so we can put more atoms. Three body losses are a little bit larger, so you reach this line faster, but you see that there is sort of an overall agreement with the theory, but there seems to be a shift. Okay, so this is strongly dependent on whether we know very well the scattering length or not. We always pretend we know it very well, but we should be careful. So maybe this is just due to some systematic error, but maybe there is really a shift in where we locate this critical line. So here, above this data point, we always see self-bound droplets, and here below this critical line, we see that we have so far only a qualitative agreement with theory. In the 10 seconds that I have, I will use maybe 2 minutes. I want to give you a little perspective on this. So everything I showed so far to create these liquid droplets is with dipolar atoms, okay? But I want to show you that it's not always, you don't need a dipole-dipole interaction. What you need is simply to have an attraction and a repulsion. Actually, this was proposed before. I should have the reference again by Dima Petrov, as I told you. So his proposal is to have two species, so no dipole-dipole interaction, only contact interactions, okay? But now two species. So here I put them as green and red. One green species that they repel each other, so two green atoms repel each other. Two red atoms also repel each other, so you have repulsive interactions between identical atoms, so intra-species interactions are repulsive. But then you have an attraction interspecies, so a red and a green atom attract each other, okay? So you see that before we had only a single species, but we had two interactions. We had the contact interaction that was repulsive and the dipole-dipole interaction that was attractive. Now I have, it's always the same interactions, but because I have two different species, I also have two mean field interactions. One that is the intra-species and one that is the interspecies that is repulsive. And you can show that beyond mean field effects are also repulsive, and they have exactly the same density dependence as in the case of dipole-dipole interaction. So of course, if I keep only one species, I will have a gas because they are repulsive, there is nothing you can do. But if now you consider the two species, look at the energy density as a function of density, let's pretend the two have the same density and they have the same mass. Now I have repulsive repulsive contact, no dipole-dipole, sorry, repulsive contact interaction for two atoms, for the other species, intraspecies is repulsive. Now I have interspecies that is with a coupling constant, but G now is negative, okay? Because it's attractive. And then you have exactly the same thing, and then you have the beyond mean field term. And then you have actually exactly the same thing, where now alpha mean field is basically equal to G11 plus G22 over 2 minus absolute value of G1. Okay, so G12 is needed. Okay, and so if G1, the absolute value of G12 is if the absolute value of if the absolute value of G12 is a little bit higher than this, then the mean field interaction is attractive, and then the BL mean field is always repulsive, and I have exactly the same thing. And actually, in experiments with contact interactions only with potassium 39, but two spin states, they could exactly make this kind of mixtures in Barcelona, near Barcelona, and in Florence with exactly the same atom, and they saw exactly the same thing where you have this liquid to gas relation. Okay, with this I want to thank you for your attention. If you have any question, you can ask me for my email, and you send me an email with your question. I will answer it. So I would like to conclude on this.
Questions? Yes?
Okay, if you do the experiment where you switch off the trap, how good does the initial trap resembles the density distribution of the drop?
So you have to make a droplet initially in the trap, right? If you put the atoms if you put the atoms side by side, and they will repel each other, you will not form the droplet. So you have to have them at least head to tail in the trap initially. Okay, so you have to preform the density distribution. The exact ratio doesn't matter. So
okay, so as long as you go.
yes, I will show you the phase diagram. This is the important part. As soon as you go into this region here where you have a droplet, it's fine. Okay. If you start from here or from here where you have many droplets, it doesn't work. But the exact trap that you have, it doesn't really matter. The important thing, of course, is if you don't have the exact trap, there will be a little bit of heating because the density adapts a little bit. But this is just qualitative.
But this is not the reason why it holds no longer than 60 milliseconds or something like this. So could you improve on this if you...
No. It's really 3 body losses. It's for our experiments. In the case of erbium and in the case of potassium, it was really important to sort of gently release this droplet such that it doesn't excite some crazy excitations that drive some losses of atoms. In our case, it's sufficiently robust. But for potassium, for instance, the maximum time they've seen is maybe 10-15 milliseconds lifetime. But we are 10 times longer lived, so this is not a problem for us.
You said for the quantum of droplets that if you turn off the trap, so the system keeps his state, but you still have the magnetic field. It's kind of a trap.
No, it's not a trap. So here is as a function of z. What I have if I have an optical dipole trap. Okay, so this is the potential V of z. If I have an optical dipole trap, only this, I have something that looks like this. Okay, and the atoms are trapped. Now, in reality, you also have gravity, so it looks like this. In fact. Okay. And if I release the trap, then I have something that looks something like this. Okay? I switch off so I'm not talking about the magnetic field, okay? So if I switch off the laser, now potential that is like this. And the only thing that we're doing is to add a force such that the potential is really flat. And there is no curvature in the potential, in the external potential that the atoms feel. Okay? So this is a constant force. This is not a restoring force that would trap the atoms.
Okay. So please imagine that you have a mixture of two species with dipole-dipole interaction. In such case, what is the situation or probably droplet?
Well, I think it will depend on the. So let's go to the simple case where the two species have the same dipole. So then the two isotopes of dysprosium, for instance, are almost the same mass, such that the dipole-dipole interaction is the same. Then you have to take into account the intra-species contact interactions. So there will be 3 scattering lengths in the problem, but there will be some, in some parameter range, you will have a solution that binds all the atoms together. There are probably some regions where only one species can be bound to itself. For instance, if you have strong repulsive interspecies interaction, they will just split up because it's always more favorable. If you have attraction or repulsion that is not too strong, they will attract each other thanks to the dipole-dipole interaction. So there will be a complex phase diagram where they're miscible, immiscible, and when they're miscible, maybe they can form a self-bound state or maybe not. But it's possible that you will have a self-bound state in some situation, but experimentally, what is exactly the scattering length, we don't know. So we have to measure all these scattering lengths independently, so this is hard. But it's not impossible.
Maybe a simpler case, but interspecies entropy is attractive, and the intraspecies is repulsive interaction.
Yes.
And dipole-dipole interaction is small. This epsilon d is very small to 1. Maybe this can be because in such a case dipole-dipole interaction just small correction to the non-dipolar, the non-dipolar
But so yes, but the experimental situation, I don't know if I can do that. I have to measure the scattering length experimentally. You have this Feshbach resonances, but you can only tune on a small parameter range, so I don't know if we can have this situation in the experiment. But theoretically, it's still interesting to study it. More
So
questions?
these droplets are another phase of the matter. So there is a
So-
transition phase between.
Yes, so I have an opinion. So we decided to call it a liquid for the following reason. So a liquid is used in many different cases. And we use it in the sense of like water becomes a liquid at 100 Celsius degrees. So it's liquid in the sense that if you put it in an infinite volume, the density doesn't go to 0. So an order parameter for this phase transition would be the density in infinite volume, the peak density in infinite volume. It's a self-bound state, it has a negative chemical potential, the compressibility has a discontinuity at the phase transition in some parameter range. For liquid, sometimes people require for something to be called a liquid that you have a short range correlation function with typical oscillations, and it's actually probably not the case in our quantum bucket. So it's liquid in the sense that what differs between a gas and a liquid is the density and the compressibility. And remember that for water, actually, there is a point where there is no phase transition between gas and liquid. So it's in this sense that we call it a liquid. It's a different. You can define an order parameter that differs between the gas and the liquid phase. That's why we call it a liquid. It's not a. It's sort of. this is a very surprising state because it's weakly correlated. The interactions are not very strong. If you ask Stefano, he can go to much stronger interactions in theory. But still, even with weak interactions that give you weak correlations, you can still have a liquid. And this was very surprising. Actually, the physics is known since 1957, right? But it's only recently that people realize that this is possible. Yes?
What if we have impurity in this boson condensation? We have also see the droplets there?
If it's just an impurity, yes. So this connects to the question of Delali. Yes. If the impurity doesn't interact very strongly with the droplet, it will not have a very strong effect. So the main effect that the atoms from the droplet will see is the interaction with the other atoms of the droplet. So for instance, we've considered if I put a few fermions inside the droplet, then because there are very few fermions, they don't modify too much physics of the bosons inside the droplets. And what is very interesting is that because the trap is so shallow, you will never be able to, because fermions you can put only one per state. Bosons, they all gather into these self-bound states, but fermions you can put only one, or you put only a few because there are only a few states that exist in this spectrum.
So if not, there is a coffee break waiting
Yeah.
for us. And so that's it.
Thank you.
So we complete here in
25 minutes.
25.
Yes. I will. Yes, write me an email. But be sure to write
ما شاء الله. Yes. مروحة وي كباس يا فاطمة الله يسلمك
Yes. In the general case, yes, you have to and beyond infiltrate is not strong enough, so you have
أبي فيها زوم اوبتيكال تروندو
still thin because the both structure is